Hey folks, got our last example for Gauss's law and conductors. And let me explain what I've drawn here. I've got a long or a sheet of charge that has a surface charge density sigma, which I will give you a number for shortly. I have a conductor that has a total area charge of positive 3 sigma, but that's going to be split up between the left surface and the right surface somehow. And by the way, we'll label those surfaces A and B. But I don't know how it's split up yet. Okay, it's not half and half. And then we have another sheet of material, a plane of material that has a charge area, a density of negative 3 sigma. And just for fun, we'll give sigma a number. Let's say sigma is 5 nanocoulombs per meter squared. Okay, so that's our charge density for sigma. So here's what we're going to figure out. Two things. One, of this 3 sigma on the central conductor here, how much goes left to the A and how much goes right to B? And secondly, what's the electric field at every location? Okay, and we'll do it both in terms of sigma, and then we'll actually plug in our calculators and get some numbers. Okay. Now, in order to do this, first of all, if you need a moment to pause the video and copy the diagram, that would be the best time to do that. And draw it pretty big because we're going to be doing our work within the picture. So make sure you draw the picture pretty big. All right, hopefully you got that drawn. So here's the deal, okay? Let me start with the electric field here. What does it have to be if your conductor is in electrostatic equilibrium? Well, that has to be 0, and we're going to use that fact in a bit. So that electric field at that spot is 0, okay? Now, the next spot I'll look at is the far, far, far left, so over here somewhere. Okay, so here's the deal. You've got 3 different things making fields. You got this positive sigma, which would make a field pointing left. You got this positive 3 sigma, which would make a field 3 times bigger to the left. And you have this negative 3 sigma, which would make a field toward it to the right. Okay. Now, it doesn't matter how far away you are from these conductors. We're assuming they're large planes of charge, and we're relatively close to them compared to how big they are. So in essence, what you have here is, imagine you look at all the charge to the left of this point. Well, there isn't any. And you look at all the charge to the right. Okay, well, if I draw this, that cuts through the entire picture. I don't want to draw the way through the picture. It'll be a mess. But imagine this area kept going all the way through the picture. How much charge would you capture? Well, it'd be positive sigma plus 3 sigma minus 3 sigma. So that'd be a positive sigma. So for a plane of charge, electric field, okay, is sigma over 2 epsilon naught. Well, that's what we have here. We have sigma. So our electric field would be left, okay, because there's a positive charge here making the field and there's no charge there at all. So there's a field left. So our net field would be left, and it would be sigma over 2 epsilon naught. Now, if you plug in sigma is equal to 5 nanocoulombs per meter squared, 5 nanocoulombs is 5 times 10 to the negative 9th. So if you plug in a 5 times 10 to the negative 9th for sigma, and epsilon naught is 8.85 times 10 to the negative 12th. If you plug all that in, you get, I get 28.2, and that would be newtons per coulomb. So this is our electric field anywhere to the left of that sheet, okay? Now, we're basically going to do the same process at each other location. So how about between the left-hand sheet and the conductor? So like here, let's say. So here's what you do. You say, well, I have some area to the left. How much total sigma do I get there? Well, I get a positive 1 sigma to the left. So that's going to make a field pointing to the right, positive. To the right of this thing, if I imagine this area going all the way through everything in the picture, I capture a positive 3 sigma and a negative 3 sigma, which is 0. So my electric field here, my net electric field, would be a sigma over 2 epsilon naught, but now it's to the right, and it's also 28.2 newtons per coulomb. Okay, so that would be my electric field in that location. Well, as we said a minute ago, we know the electric field there in the middle of the conductor, or with anywhere within the conductor, is 0. So here's what that means. That means the total charge, if I draw an area that goes forever to the left, whatever charge is in there has to equal, if I draw an area that goes to the right forever and cuts through everything in my picture, this charge that's within this thing has to equal this charge that's within that thing, because those two, the electric fields created by those two charges have to cancel. So we're going to write that as an equation. So I know that's this sigma plus A. That's the total charge that I get in this, to the left of this thing, has to equal B plus negative 3 sigma. So let's write that down here. So I know that sigma plus, and I'll label it sigma A, that's the left-hand surface of the conductor, has to equal sigma B minus 3 sigma. So all I'm doing is saying I know that this charge on the left has to equal this charge on the right, because the field made by this charge on the left has to cancel the electric field made by this charge on the right. Okay. Now I also have a second equation. I know that sigma A plus sigma B has to equal 3 sigma. Okay, because the conductor has a total of 3 sigma and it's got to split up somehow between A and B. So I know that sigma A plus sigma B is equal to 3 sigma. Now, if I take the first equation and I just rearrange that, if I move the sigma B to the left, I'm going to have sigma A minus sigma B. And then if I move this sigma to the right, I get negative 3 sigma minus sigma. Well, that's minus 4 sigma. And now if I take those bottom two equations and add them together, I've got 2 sigma A has to equal negative 1 sigma. So sigma A has to equal negative 1/2 sigma, which would be negative 2.5 nanocoulombs per meter cubed. And sigma B has to equal 3.5 sigma, which would be positive, let's see, 5 times 3.5 would be 17.5 nanocoulombs per meter cubed. That'd be positive. So those are my surface charge densities there, and I'll go ahead and write them in. So this is 1/2 sigma, negative, oh, was that negative? Forget. Negative, yep. So that's a negative 1/2 sigma, and this is positive 3.5 sigmas right there. Okay, now the electric field's over here. That's relatively easy. So let's say I'm right here, okay? How much total charge is to the left of that point? Well, I've got a positive 3 sigma and a positive sigma, so that's a positive 4 sigma. That's going to make a field pointing right, away from it, positives away. And then to the right of this thing, I've got a negative 3 sigma, which is also going to make a field to the right, okay, because it's negative toward. So what's my total? Well, my total electric field would be 7 sigma over 2 epsilon naught to the right. And if I plug that in the calculator, I got, when I did that, I got 197.7 newtons per coulomb. So that is the net electric field between those two areas. And then finally, out here, I've got no charge to the right. To the left, I have a negative 3 sigma, a positive 3 sigma, and a positive sigma. So that's a positive sigma. That'll make a field to the right. That field will be sigma over 2 epsilon naught to the right, which we already calculated that before. That's 28.2 newtons per coulomb. So that's the electric field in that region. Now, one last thing I'll mention about this. If you look at the far outsides of our picture, to the far left, we have a 28.2 newtons per coulomb field to the left. To the far right, we have the exact same field to the right. That will always be true. Because if you think about it, if I were to crush all these together, what do we end up with? Well, it simplifies down to, we got a sigma, a 3 sigma, and a negative 3 sigma. It's like you have a single plane of charge. That's a positive sigma. So the field would be sigma over 2 epsilon naught that way, and sigma over 2 epsilon naught that way, which is our 28.2 and 28.2. So you can look for, that can be helpful to say, okay, you can pretend these are all one big sheet, and on the far outside, I'm going to have whatever that total sigma is divided by 2 epsilon naught as my field out there. And it's going to be equal and opposite field on the far right and the far left. Okay, so I hope that video was helpful, and that concludes Gauss's law. Thank you very much.